All right, let's go ahead and get started. We have lots of dense material to get through, so but it is my pleasure as Emily's advisor to welcome you all to Emily Mather's master's thesis presentation with a lovely song-type title, Where Has All the Energy Gone? Quantifying Advective Energy Fluxes with Dense Tower Networks. And this is lovely because it just very much ties this. The very first email I got from Emily 2 years ago, or 2.5 years, 3 years ago, I guess, was, my name is Emily Mather. I'm very interested in research on land-atmosphere interactions and how they impact regional weather and climate. And so, and it's one of these great kismets where we have to actually take the core thing you're interested in and really dive into exactly that exact problem, where we're really thinking about this idea of the surface energy balance based on, as you'll hear about, some of the field experiments we've done in the past. And Emily's one of the first to really kind of tie a bunch of this data together in a way that we haven't been able to with some of our earlier studies where we were just trying to get our heads around all of the petabytes of data we did collect. So I think everyone here knows Emily, but she's a pretty active member of our department. But a few things you may not know. So she grew up in Seattle, and she got her bachelor's in mechanical engineering. And then she figured things out and correctly decided that the right thing to do is to come get a degree in atmospheric science. But she graduated with that degree from Seattle University, and then spent a few years doing a couple different things kind of as a volunteer. So she was in the Peace Corps, and she was in Tanzania, where she worked in teaching math and physics. She was a member of AmeriCorps, where she worked with supporting refugees and immigrant youth in Seattle, in the Seattle area, and then was working at an institute with families that are learning and talking scholarships in Swahili. Right? And so just this really broad range of kind of excellent education and experiences that I think set her up really well to come here to now take her skills both in working with communities and being an international scholar and bringing it into thinking about a problem that we care about here in the atmospheric oceanic sciences. So I'm super happy to have her here. Emily, some of you may also know, is a cellist. She plays with the UW Community Orchestra. As I see her, occasionally cello is there instead of her at her desk. And I think you'll see something in this talk. So I went through the slides this morning and their final draft, and there's a rhythm and musicality to the way that things are presented here, right? There's a lot of material that we have to talk about to get you all to the same page that Emily's at, and I think you'll see that musician's eye to how to present things within this talk, and I'm going to turn it over to you. Thank you.
Yes, and I just remembered that I did a slide that I want to be visible, so.
So you're into improv now.
Yeah. Don't forget to
jazz. I just wanted to check there. So let's go back to this.
Is the mic unmuted?
You're correct, it is muted. Thank you. And thank you, Walker, for that introduction. Can everyone hear me? I've been known to speak quietly, so if you can't, give me a heads up. Yes, thank you, Walker, for the introduction, and thank you all for being here today for my talk. The goal of this study is to see if we can improve surface atmosphere energy exchange measurements by accounting for advective energy fluxes. And I'll explain a little bit more about what that means in a second, but I want to start off by just giving some motivation for this project. So my apologies to the oceanographers in the room for the gross generalization, but many of you here study things that happen in the atmosphere. And well, we all know that the atmosphere is a fascinating place. As you might guess by this figure that's clearly chopped off in the middle, it's not the full story. So much of what goes on in the atmosphere is really driven by processes that occur at the land surface. And there's a lot going on in this figure, but really, I'm not going to talk about all of it. What I really want you to take away from this is just that land surface processes, in particular energy fluxes, or exchange of energy between the land surface and the atmosphere, is a really important driver of the state of the atmosphere. And so if we want to predict things like weather and climate, we need to understand what's happening at the land surface and to be able to measure those processes. So that's where my research comes in. And here now we're just going to be talking about these two terms, which is just the exchange of energy between the land surface and the atmosphere. So we have sensible heat flux, which is the direct heating of the air at the land surface, and then moisture flux or latent heat flux, which is the evaporation of water at the land surface, which is then later released as heat in the atmosphere when that water condenses. So if you're interested in measuring these fluxes of energy from the surface, you might use the eddy covariance method. Maybe you're interested in studying a forest, and so you put up a flux tower. And some wind comes along, and maybe the sun heats up the surface, and so some combination of the wind and the surface heating is going to lead to some turbulent eddies that transport energy from the surface up into the atmosphere. And we want to use that flux tower to measure how much energy of those two types, sensible and latent heat, are being transferred. So we can use this equation where Fc is the flux of either temperature or moisture, and that is equal to the air density times the covariance of the temporal anomalies of your vertical wind velocity, which we measure using a sonic anemometer, and either temperature or moisture. If it's moisture, we measure that using the gas analyzer. So we just talked about this equation, the flux of temperature and moisture. If we want to turn that into energy fluxes, we just have to do a little bit of math. So as I mentioned, C in that equation refers to temperature, or Q, the water vapor mixing ratio. And to get sensible heat flux, we just have to take the flux temperature and multiply that by the specific heat capacity. So H is sensible heat flux, and then lambda E, or latent heat flux, is just the flux of moisture times the latent heat of vaporization of water. And then I want to define the Bowen ratio here, which is just the ratio of sensible to latent heat flux, and that will come in to play later on. So, so if you want to measure the exchange of energy at the surface, you are going to need to measure 4 main terms, and that is net radiation, ground heat flux, sensible heat flux, and latent heat flux. So all of these energy terms can go in either direction, but these are the directions that they most often go during the day, and is also the direction that we kind of assume are positive. So net radiation is considered positive if energy is going into the surface, while G, H, and lambda E are considered positive if they're leaving the surface. That's just by convention. So we know that energy is conserved, and so energy coming into the surface should be equal to energy going out, and we can write that this way, where on our left-hand side of the equation we have Rn minus G, and those two terms together we sometimes call available energy, and that should be equal to our sensible and latent heat flux is away from the surface. But what we find when we measure these using the eddy covariance method is that typically available energy is more than sensible plus latent heat. And that doesn't make sense because physics says they should be equal. So, but we're going to rewrite this and say we have a measured imbalance, and that is equal to our net radiation minus G, H, and lambda E. And so to get a sense of what each of these terms look like, we have net radiation is usually the largest energy flux term, and then we have G, H, and lambda E, and then there's this imbalance. And you can see in this spot that the imbalance is pretty significant. At most flux sites, it's about 10 to 30% of available energy. And so we really need to account for this and figure out what's going on there. And another thing that has been observed is that imbalance tends to be greater over heterogeneous ecosystems when you're measuring over a heterogeneous surface as compared to a more homogeneous measurement area. So, where has all the energy gone? There are a number of different known and theorized causes of energy imbalance when we're measuring using the eddy covariance method. These generally fall under 2 categories. One is data collection and processing errors, and the other one we'll call additional energy fluxes. Data collection and processing errors are not the focus of this presentation, so I'm not going to go into detail here, but know that many of these can't really explain the sort of systematic imbalance that we see, because most of them are random. So they might cause imbalance at certain sites, but they don't explain why we see this consistently positive imbalance across nearly all eddy covariance states. So we're going to focus on additional energy fluxes. So I talked about these four terms of our surface energy balance. And usually with the eddy covariance system, we assume that the turbulent fluxes of H and lambda E, which is what I described a few slides back, are equal to the entire flux of sensible and latent heat from the surface. But really this is a pretty simplified one-dimensional approach to the surface energy balance, and the fact is that we live in a three-dimensional world. So maybe we need to take a three-dimensional approach. So here's a three-dimensional surface-atmosphere exchange. There's a lot going on in this figure as well, so I'm going to orient you a little bit. Here's a flux tower in the middle. Here's our coordinate system where Z is perpendicular to the surface, X and Y are in the plane parallel to the surface. Sometimes we orient X so that it's parallel to the mean wind, but not always. And then here is a box which we'll call the control volume around the flux tower. And the height of the box is the measurement height of the flux tower, and then we can say that it extends in L meters to either side of the tower. And so, so what we're measuring with the eddy covariance system is the turbulent fluxes of H and lambda E going out the top of that box. But really, what we want to know is the energy leaving the surface, so essentially what's coming in the bottom. So those are sometimes equal to each other, but there are a lot of other fluxes that could be occurring that might make them not equal to each other. And those are often assumed to be zero because they often are quite close to zero, but sometimes they're not. And so that's what we're going to be focusing on today. So the first one of those energy fluxes that we're not going to talk about a lot here, but just to mention, is storage. So you could have some change of the amount of energy inside your box that is, so some of the energy that's released from the surface might not be going out the top. We could also have horizontal advection. So that is wind blowing energy into or out of the box from the sides here or here. And then the last is vertical advection. And so that is if we have a mean vertical wind that could be moving energy into or out of the box through the top. We typically assume that the vertical wind is zero because it is usually very small, but there are certain situations in which it is large enough that it can lead to a vertical advective flux that we need to account for. In particular, so before we looked at this where we have small eddies that are swirling around, but you can have large-scale circulations that might lead to a consistent downdraft or updraft at your measurement point over the entirety of your measurement period, or at least an uneven sampling of updrafts and downdrafts. And that in particular can happen if you have a heterogeneous land surface where maybe one area is warmer than another, and so that could lead to an updraft in one area and a downdraft in another, and these large-scale circulations that can transfer energy between the surface and the atmosphere, but that energy transfer is not captured by the eddy covariance system. Okay, so now we're going to get into some math. I'm going to go through this pretty quickly because I don't want anyone to fall asleep. Just note I will be putting the assumptions for each, we're going to simplify this quite a bit. I will be putting the assumptions for each simplification at the top, and that's really the important thing for you to pay attention to. So the first thing that we're going to assume is that our control volume is horizontally homogeneous, or at least that the measurements taken at the flux tower are representative of the horizontal plane in which they are taken. So if we do that, all of these integrals here are essentially just a horizontal averaging, and we can get rid of them. Horizontal homogeneity can also let us get rid of these terms, which are the horizontal turbulent flux divergence, which are also very small or negligible under a horizontally homogeneous condition. Next, we're going to assume that our flow is incompressible, so we can apply the continuity equation, which is in the upper right-hand corner there. So and we're going to move these equations to the side here and pull out just these terms, expand them using the chain rule, and then these terms, we'll see they kind of look at the right-hand side of the continuity equation, so we can make that substitution there and stick this back into our main equation. Okay, so now we're going to move this back to the middle, and our next assumption is that v bar is 0. So the way that we do that is we orient our coordinate system so that the mean wind, the x coordinate is oriented along the mean wind, and so you don't have any mean wind in the y direction. So v bar is 0. And then we're going to integrate these terms from the surface up to the measurement point, Zm. And we know that air can't come out of the surface, so our W bar at the time of 0 is 0. So those go away. Our last assumption is that the profile of vertical velocity from the surface up to the measurement point is linear. So vertical velocity increases linearly from 0 at the surface up to some value, W bar of Zm at the measurement height Zm, which I think I did not specify. Mentioned that before, but Zm is the measurement height of the eddy covariance system on our towers. So if we make this substitution here, then we're able to integrate this term, and that leaves us with the vertical wind velocity at Zm times a vertically averaged value of c. So the angled brackets mean vertically averaged, as opposed to overbar, which is temporal average. And then if we just rearrange that equation, we end up here. And so we have 4 terms now. We have storage, horizontal advection, vertical advection, and turbulent fluxes. So turbulent fluxes is what we normally measure. Storage is measured at a lot of eddy covariance sites, and again, it's just not the focus of this study. So these are the 2 that we care about here. And so later on in the presentation, you'll see these 2 equations come up again. But first, I want to talk about the data that I used to calculate these advective fluxes. So for those of you who are unfamiliar, Cheesehead is an acronym which comes to you from the brilliant mind of Ankar Desai. It stands for Chequamegon Heterogeneous Ecosystem Energy Balance Study enabled by High Density Extensive Array of Detectors in 2019. And this was a field campaign that took place in northern Wisconsin in 2019, as you might guess. The main goal of this study was to understand more about the energy balance of heterogeneous ecosystems. As I mentioned before, we find that energy balance tends to be worse when we're measuring it over heterogeneous ecosystems. And then this was enabled by high density extensive array of detectors, so there are a lot of measurements taken during the Cheesehead campaign, but I'm going to focus specifically on the measurements taken at 18 flux towers that were arranged in a 10 kilometer by 10 kilometer study area. So those are all shown here on this map. So all of the data that I used was measurements taken at these flux towers. Flux towers usually measure vertical wind velocity, temperature, and water vapor mixing ratio at 10 hertz, and then that can be used to calculate sensible and latent heat fluxes. Net radiation and ground heat flux were also measured. And then wind speed and direction were measured at the top of each tower, and profiles of temperature and humidity were measured at most of the towers at 3 levels, close to 2 meters, 12 meters, and 33 meters. Those heights vary a little bit at some of the towers, and some of the towers only have 1 or 2 of those levels, but most of them have 3 levels around those heights. So that is the data that we used. And so now I'm going to go over the 5 questions that I am trying to answer with my study. The first is, can we derive reasonable estimates of advective fluxes from the network of tower measurements? Second is, how does the Bowen ratio of the advective fluxes compare to that of the turbulent fluxes? And I'll explain a little bit more later on about why we care about that. And then, how do the advective fluxes vary with time and atmospheric conditions? So here we're trying to get at sort of what is the nature of advection, does it matter, and like how much and when? And then is energy balance closure improved when the advective fluxes are included? So we are calculating these advective fluxes because we think that maybe they are part of the reason for this energy imbalance. So we would expect that if we include them in our total energy balance, that would improve the.
Is there any reason why you would expect the advective fluxes to be generally positive or negative as opposed to 0 on average?
Yes, essentially.
Maybe you're going to get there.
Yeah, well, yeah.
Like you mentioned there was a systematic bias.
Yes.
And so I'm just wondering,
yeah, so if you think about
hypothesis for why advective fluxes would explain a systematic bias rather than a random bias?
Yeah, so if you think about like the surface as most of the energy imbalance occurs during the day. So if you think about the surface as being warmer than the atmosphere above it, vertical advective flux. So like whether you have like a positive vertical wind moving warm air up or a negative vertical wind moving, that's going to move cold air down. So both of those are positive vertical advective fluxes. So regardless of which way you have this mean vertical wind, you're going to have a positive vertical advective flux. And of course that's different if you have a different, like if you have warmer
So it's
air
on
above.
nighttime you expect there to be convective fluxes up is essentially what you're saying. Or sorry, daytime.
Yes.
You expect there to be
Daytime,
convective fluxes
yes.
up.
Because that is when, I could go back really quickly. Actually, that's a lot of slides. I'll show it at the end, but
Okay. I'm probably jumping ahead
but-
on your story.
yeah, so most of the imbalance occurs during the day, and like if you think about the way that these large-scale circulations are moving energy, they'll generally be moving energy away from the surface during the day when the surface is warmer than the atmosphere.
Cool, thank you.
Yep. Okay. And then, how sensitive are the calculated advective fluxes to variations in the method used to calculate them? So I, as I was working on this project, I kept kind of running into decision points where there were different ways that I could do these calculations, and I wasn't always sure what was the best way, and so what I ended up doing was kind of creating like a matrix of different variations and calculations, and ran all of those to get a sense of how sensitive the calculations are to these different decisions, and the idea is that that could, in the future, help someone figure out which ones do we need to figure out how to do like right, and which ones don't really matter. Okay, so the rest of my presentation is sort of organized into 3 sections. The first is where I'm just calculating the advective fluxes, and I'm trying to answer those first 3 questions. The second part is the energy balance analysis, and then the third is that sensitivity analysis. And so those are the questions that I'm trying to answer in each of these sections. So, part A, advective flux calculations. This is the equation for horizontal advection that we found earlier. So in order to calculate this, we need a profile of vertical wind. You'll remember that we have measurements of horizontal wind. Well, we have measurements of horizontal wind at the top of the towers, but we need a profile from the surface up to the top of the tower in order to calculate horizontal advection. So applied just a wind profile model above the canopy. I used a pretty standard logarithmic wind profile, which is typical for boundary layer wind profiles. In the surface, or in the canopy, we used an exponential profile, and then again a logarithmic profile in the bottom 10% of vegetation, which uses properties of the surface rather than of the vegetation, essentially. Okay, and so then we also need profiles of the horizontal gradients of our tracers, T and Q. So remember, we have measurements of T and Q at 2, 12, and 33 meters. If you think about all the measurements at all the towers at 2 meters, and imagine those in a horizontal plane with each other, and then we kind of turn our view to look from the top. And so this is the location of each of those towers. We have T and Q measurements at each of these points. We also have wind direction measured in each of those places. And so then I used a 2D interpolation method, specifically the SciPy RBF interpolator, to interpolate T and Q to points 1 kilometer upwind and downwind of each of the towers. And then I essentially just assumed that the gradients between those points are linear, so that allows me to calculate dc dx. And then if we kind of turn our view again to look from the side, we now have dc dx at each of these points here, each of the measurement levels, and then we assumed a linear profile in between each of those measurement heights to get a full profile of dc dx in order to be able to numerically integrate up to the measurement height. There we go. Okay, so vertical advection, there's our equation. We need W bar at the measurement height. This is just an example of about 3 hours of 10 hertz vertical velocity measurements. And then the red line shows the 30-minute averages of those data. And you'll see that W bar is really close to 0, and that's part of the reason that we often assume that vertical advection is negligible. But when you have a large enough gradient of C, vertical gradient of C, then vertical advection can actually be significant. So we do still have to account for that. Our C of Zn, that's just the measurements of T and Q at the top of the tower, and then we need a vertically averaged value of C. And so that, again, we have measurements at 212 and 33 meters, and I just assumed a linear profile in between those to get a full profile, and vertically averaged that. Okay, so here are some results. Let's look at the distributions of the advective fluxes. So you can see on the right-hand side here, sorry, left. On the left side, we have horizontal advection of sensible heat, horizontal advection of latent heat, vertical advection of sensible heat, and then vertical advection of latent heat. And one of the things I want you to notice about this is if we look at the x-axes, the scales here, you'll see that vertical advection is nearly an order of magnitude larger than the horizontal advection. And sometimes our vertical advection is large enough that it's not particularly realistic. Like there are times when it's significantly larger than the available energy, and that doesn't really seem physically possible. Another thing I want you to notice is that we do find that our advective fluxes are pretty much evenly centered around 0, and so this kind of goes to what Larissa was asking about. If we expect the advective fluxes to improve energy balance closure, we would expect them to be more often positive than negative, but we don't really find that to be the case here. So Bowen ratio closure. I mentioned before that I would talk about why we care about the Bowen ratio of the turbulent and advective fluxes. Just a reminder, our Bowen ratio is the ratio of sensible to latent heat. And if we're measuring these fluxes at an covariance site, we'll often measure our available energy in brown as being greater than the sum of the turbulent and latent heat fluxes. And there are certain applications when you need your energy fluxes to be balanced, and like if you're going to put this data into a model. And so the most common way that people do that is force the energy balance to be closed by using what we call the Bowen ratio closure method, which essentially just maintains the Bowen ratio but sort of extends the sensible and latent heat by the same ratio in order to have a fully balanced energy budget. So if that is the case, and if we think, or if this is an accurate representation of the actual energy fluxes, and if we think that the advective fluxes contribute to this energy imbalance, then we might expect that the Bowen ratio of our turbulent fluxes would be a good estimate of the Bowen ratio of the advective fluxes. So let's take a look. Not really. Here's a one-to-one line. So if the Bowen ratio of the advective flux, or of the turbulent fluxes was actually a good representation of the Bowen ratio of the advective fluxes, all our points would be lined up along there, and they're not. And here's the actual best fit line to that, which of course is kind of hard to, find meaning in a regression line when you have this much scatter, but what the slope of that does indicate is that the Bowen ratio of the turbulent fluxes is often larger than the bone ratio of the advective fluxes, which would indicate that if we're using the bone ratio closure method, we are overestimating sensible heat fluxes and underestimating latent heat fluxes. Okay, so I also wanted to look at the deal cycle of all of the advective fluxes. So each of the lines on these plots represent one of the towers. And again, there are a couple things I want you to take away. One, look at the y-axes. The scales are different, otherwise it's going to be a little bit confusing if you don't recognize that. But we see this pretty clear deal cycle in both of the latent heat fluxes, and not nearly as much in the sensible heat fluxes. But it is interesting that with the latent heat, they have this clear deal cycle, but it's some towers we have positive, while others we have a negative midday peak. The other thing is, because of that cycle, latent heat very much dominates the advective fluxes during the day, whereas sensible heat is more important, but similarly important to latent heat during the nighttime. And then this is just to show a couple of specific towers. And this is to show that for most of the towers, the midday peak of vertical and horizontal latent heat fluxes is of opposite signs. And then this plot is showing the relationship between atmospheric stability and our total advective flux. So on the bottom we have Z over L, which is the atmospheric stability parameter. When it's negative, so on this side of the plot, it's an unstable atmosphere. Positive is stable atmosphere. And what we see is that under a weakly to moderately stable atmosphere, we have the smallest magnitudes of advective fluxes, and then advective fluxes increase with increasingly stable or increasingly unstable atmosphere from there. And the reason that this matters is because a similar pattern has been observed between the relationship of the stability parameter and imbalance. So that indicates some kind of similar mechanism driving imbalance and advection, which might indicate that, or like lend some evidence to the idea that the advection is part of the imbalance that we're observing. Okay, so just a quick summary. We asked whether we can reasonably estimate advective fluxes from the network of tower measurements. Sometimes, but we did find that the vertical advection seems to be overestimated. How do the bone ratio, the advective and turbulent fluxes compare? Bone ratio of the turbulent is maybe bigger than advective, but there isn't really a clear relationship there. And then how do the advective fluxes vary with time and atmospheric condition? We found that latent heat advective fluxes dominates during the day, and then sensible heat matters more at night. And the advection is smallest under weakly to moderately stable conditions. Okay, part B. So here we're looking at whether these advective fluxes improve energy balance closure. So I want to define a few terms here. The first, we already saw this equation for imbalance. This is just a little bit different in that have the subscript MA to denote that this is no advection. This is the imbalance without the advection terms. And then I want to specify that these terms are the turbulent, sensible, and latent heat fluxes measured at the towers. And then we also included this storage term, which was included in the data set. That is part of the total surface energy balance, so included that as well. Our imbalance with advection is the same as without, except that we also have our 4 advection terms there. And then we have IMBAH, which is the imbalance with only the horizontal advection included. And that is because, as we saw, the horizontal advective fluxes are much smaller than the vertical advective fluxes. And so we wanted to look at what happens if the vertical advective fluxes really dominate the story. And so we wanted to see what is happening with just the horizontal advection. And then when I define this term here, EBI, which is energy balance improvement, and so that is essentially just a percent difference between the magnitudes of the imbalance with and without advective fluxes. So this term is positive if you have if the energy balance is improved with the inclusion of advective fluxes, and negative if the magnitude of the imbalance is greater when you include the advective fluxes. Okay, so the first thing we found was that the energy balance improved at 6 out of the 15 sites for which we were able to calculate all of the advective flux terms. In this figure, ooh, you can't see the blue at all on there. Okay, well, on my screen, this area is blue. And that denotes this line is a 1-to-1 line, this is 1 to -1, and so each of these points represents one of the towers, and the towers in this region showed an overall average improvement in surface energy balance. So the magnitude of their IMDA is less than the magnitude of IMDNA. The towers up here, there are 5 of them, showed overall increased energy imbalance. And then these ones down here, we can kind of think of as being like overcorrected. We end up with a negative imbalance that is greater in magnitude than the initial imbalance without the advective fluxes. If we make this plot with just the horizontal advective fluxes, we see a very different story. As we saw, the horizontal advective fluxes are much smaller than the vertical fluxes, so they just didn't have nearly as much of an effect on the overall energy balance. The gray lines show just plus or minus 10% from the 1-to-1 line. So any point that is like between the gray and the black lines had less than a 10% improvement or worsening of the energy balance. So we do see improvement of more towers in the case of just including horizontal advective fluxes, but the improvement isn't actually that great. Like, even though these towers improve somewhat, they still have a pretty substantial energy imbalance. Okay, so this plot shows the deal cycle of the percent of site hours that are improved at each time of day. So instead of looking at energy balance over the entire study, this is looking at each measurement period and seeing whether the energy balance improves or is made worse at that time by including the advective fluxes. So the blue bars show the percent of site hours that have improved energy balance closure. The gray is the EBI is less than 10%, and then red is EBI less than negative 10%. So gray is in between negative 10 and 10. So again, we're not seeing that really clear improvement. In fact, it gets worse a lot of the time. But we do see that energy balance improves more often during the day, especially in the morning than at night. So that's interesting. This is the same plot, again, with just horizontal. And I think one thing that's worth pointing out here is that the difference between day and night is much less. So that indicates that maybe the vertical fluxes are sort of part of the problem at night. So when we take those out, we don't see nearly as much of a difference between the improvement during the day and night. Okay, so in summary, did the energy balance improve? No, but sometimes yes for a few of the towers and at certain times, but overall no. Okay, so part C, the sensitivity analysis. So I told you that I ran a bunch of different variations on these calculations. I'm not going to go through everything in here. If you want to know more, you can read my thesis. But just point out, these are kind of like the main case. So all of the results that I showed you, those are that is the method that I used there. But I'm going to talk about differences We tried different interpolation methods and then also a different way to calculate eddy bar. So the interpolation distance, essentially, we chose 1,000 meters up and downwind of the towers as the distance to interpolate the values of T and Q to, but we could make that closer or further away from the tower. And what we find is that as the interpolation distance gets further from the towers, the advective flux estimates get smaller, and then the same as we get smaller advective fluxes. So this indicates that maybe this matters and we need to think about kind of like the mechanism or the reason for choosing that distance, and it also indicates that maybe having a higher resolution of temperature and humidity measurements might lead to increased horizontal advection estimates. Yes?
This is going to sound stupid, Emily, but I'm going to ask it anyway if you don't mind. Does 500 meters present itself as sort of a Goldilocks zone here because the eddies get disguised in advection best at that distance? Because I think at small scales, everything's happening because of eddies, and at large scales, everything's happening because of advection. So is there a cloak and dagger thing going on around 500 meters?
Yeah, well, so the reason we chose 1,000 meters was the idea. So if you do kind of just a basic scale analysis, you have wind moving at 1 meter per second, and over a 30-minute averaging period, those eddies will move 1,800 meters, so roughly 2 kilometers. So that's why we chose that, and the 30-minute time period, that's based on sort of like time when we see sort of a drop-off of eddies of that scale moving energy on the surface. But there are also other studies that have indicated that temperature differences on the hectometer scale are kind of the most significant for horizontal advection. So I don't really know, but I think this is something that maybe needs to be looked into further if people are going to use this method going forward. I don't know if that answered your question.
I don't know if my question was reasonable, so I'll take it.
Eddy fluxes can be important even on very large scales. In the tropics, they're very
Yeah, so this is the same plot, but here before we were just looking at the horizontal fluxes. Here we've included the vertical fluxes. So again, the vertical fluxes are kind of really dominating the picture. And so this is just showing like, okay, the differences in method for horizontal flux calculations does matter for the horizontal fluxes, but for the overall advective fluxes, it doesn't matter as much. But that could be just if our vertical advective fluxes are overestimated. That could be the reason. Okay. The other sort of variation that I'm going to quickly talk about is how we calculated vertical wind. So I already kind of had the infrastructure to calculate horizontal gradients by using that interpolation method. And so here is our continuity equation integrated from the surface up to the measurement point. Again, we can integrate this and get rid of that term, just like we did before. And you'll remember that we calculated these horizontal gradients for T and Q. We can do the same thing for U and V. And then if we have U and V gradients at the top of the tower, we can essentially apply our wind profile, again, to get profiles of wind of du dx, which allows us to calculate vertical velocity at the top of the tower. What we find is that does not agree well with our measured vertical velocity using the sonic anemometer. And we know that there are issues with the sonic anemometer measurements. Sonic anemometer is really good at measuring those deviations from the mean, but the mean vertical velocity is so much smaller that it's really hard to measure accurately. And so we don't, I don't know, we don't know if the sonic anemometer measurements are all that great, but it seems like maybe this continuity approach also we don't really have any evidence to say whether one is better than the other or if either are good estimates of vertical velocity. So just a reminder, these are all the red. I've showed the different variations that I ran. If you kind of do the math here, like 2 times 2 times 5 and all that, you get 204 different variations on the calculations. So if I plot the deal cycle of all of those, this plot shows each line represents one of those different variations. The red have the advective fluxes using the continuity approach, and blue is using the sonic anemometer measurements. So we can see that within those two groups, there's generally decent agreement between the advective fluxes. Kind of as we have continued to see, the vertical advective fluxes are really kind of running the story here. And it's interesting that they follow a similar pattern during the day, but then diverge at night. So that's kind of, again, some evidence that maybe it's the nighttime fluxes that are maybe are not being estimated well. So that is all from that section. So just a quick summary. The calculated advective fluxes are most sensitive to the W-bar estimation method, and that means that maybe we need some sort of improved W-bar estimate that could be using like a wind LiDAR, or at least some way to verify whether the sonic measurements are good. So conclusions. Overall, we didn't see improvement in energy balance when we included the advective fluxes, but we do have some indication that dense tolerant networks could be used to quantify advective fluxes, but we probably need an improved W-bar estimate and maybe some denser temperature and humidity measurements. Bone ratio closure method probably isn't a great way to force closure of your energy balance, so maybe we need to look into that more and to better understand when you need closure, how to do that accurately. And then advection might not be the full story. So there's a lot of evidence that advection does play a part in the surface energy imbalance, but there are also other reasons that might, or other things that might cause surface energy imbalance, and so maybe we need to look into some of those as well. And then a little poem to end. Where has all the energy gone? Gone to advection every watt? Maybe not. Here's acknowledgements for funding and support from the DOE, Flux Management Project, and a couple of NSF grants. And then, of course, the people acknowledgements. I want to thank my advisor, Ankur Desai, for being an eternal fount of both knowledge and wisdom and calming presence during my panic over the last couple months. And then the rest of my committee, Professors Paul Stoy and Kristen Lequier, and then all of the AOS faculty, staff, and students, of course, all the support from the faculty and staff, and then just everyone for making this a wonderful place to come and learn and work every day. I think my favorite part of the day is often just running into random people in the elevator and chatting. So, yeah. And then, of course, my lab, ecometeorology lab members, both past and present. I had a really wonderful group of older lab siblings in my first year who were great mentors to me. And then it's been great to see new folks come in over my time here. And of course, my family, friends, and my boyfriend, Sam, for all their support as well. Some references and any questions?
Thank you for sharing that tour de force. As you might guess, we had lots and lots and lots of different rabbit holes to explore here in trying to come up with this approach. So open it to questions. I will say, while we have a little bit of time for questions, Emily's not going too far because she is planning to stick around for a PhD. It's going to be a completely different topic, but still focusing on surface atmosphere processes. And I think a lot of the work here is going to inform the way we go about measuring this over solar panel fields, which is our next adventure that Emily might be getting into. Questions, and students are often welcome to start. Grant.
This is a bit of a question. I don't know much about this kind of topic. Is there any reason to believe it has to balance?
Yeah, the first law of thermodynamics says energy not created or destroyed.
If we get just like temperature changes day to day, does that do enough to fill this assumption?
Yeah, so that's the storage term. Like if you think about the air between your surface and the measurement height is going to change temperatures, and so there is some energy stored there. And a lot of eddy covariance sites do measure storage, not all of them, but if you have a profile of temperature and humidity measurements, you can account for that. And it doesn't usually close the energy balance. Also, you would expect that like over the entire day, or at least over a year, that should average out to about 0, and so it wouldn't explain this kind of systematic positive imbalance that we
And just to follow up, there's probably another several hours of talk on just that S term, because that's actually hiding a whole bunch of processes, not just storage of heat in the air, but trees heat up, right? Plants use energy to photosynthesize. Soils heat up, so there is soil heat storage. And we've done a lot, so in Cheesehead we actually measured quite a few of those terms as well, and to suffice to say, yeah, that's not the whole story, but you're absolutely right. Like, you have to account for all of the processes where energy can go, and it's not quite as simple as that 1D energy balance looks like. Over here.
Hey, Emily, really interesting and wonderful job. I'm also coming from a very naive perspective about this thing, but you showed that 6 out of the 15 locations showed improvement when you included advective flux, and I was wondering that, do you have any insights about what factors might have led to that? Like something like this picture showed the presence of lake or creek or something which might be just contributing to something which the others didn't.
Yeah, so I tried looking at a few different things, just like geographic location, like if being closer to certain towers, because then you would have kind of like better estimates of horizontal gradients to see whether that improves, if you see more energy balance improvement when towers are closer to others. That didn't really give a clear signal. There's like maybe a little bit of a signal there, but not much. There wasn't really any pattern with the surface type. Like the Cheesehead domain, it has like different types of forests as well as a lot of wetlands. Yeah, exactly. It's very heterogeneous, and there are flux towers. Most of them are at forest sites, but not all of them. And I haven't been able to find any patterns between like which towers have like show more improvement versus those that don't. So that is something that I would love to figure out, but I haven't gotten there yet. But yeah, great question.
And Karen, that question?
Actually, my question was really similar, just about how you think, like, I don't know if there's a quantification of amount of heterogeneity, but if the adaptive fluxes would make more of a difference, more or less of a difference, depending on the surface type. So I guess you kind of answered this question.
Yeah, I mean, and the other studies have looked at kind of like they quantify heterogeneity and find that more heterogeneity does tend to lead to greater imbalance, and there's reason to believe that that would also mean that there's greater advection happening at those sites. Like the one thing I mentioned, we have these large-scale circulations that can occur when you have a heterogeneous surface that can drive, like you have differential heating that can drive these large-scale circulations that could be part of the advection problem. But yeah, I didn't do anything in terms of like quantifying heterogeneity around the specific towers, but that could be an interesting way forward.
Shane is next.
Yeah, again, like follow up. Because you mentioned in your equations there's some assumption about homogeneity, but does that include like circuit? Just like clarifying.
Yeah, so yes, there are some assumptions that you kind of have to make just in order to be able to like calculate stuff at all. Like we just don't have measurements at every point around the domain, but you also, so the assumption of horizontal homogeneity in the equations, that is horizontal homogeneity within your control volume as opposed to like the entire like domain around your flux tower. So it's like a little bit of a weaker assumption, but it still might not be accurate. And I have some suspicions that that assumption might be part of the reason for some of the issues that we're seeing.
That's Kieran's PhD dissertation, we just started her lab.
Yeah, good luck.
You showed a few diurnal cycles, but do you see an annual cycle where the power's out long enough? Like, does the snow-covered surface cause closure?
So the measurements were only taken between June and October. So you can't look at an annual cycle. I think I took a plot out. I had meant to put it at the end. If you look at the change just over that time from June to October, there's generally is a decrease in the imbalance during that time and kind of an increase in average advection from being positive up to about 0. So towards the end of the study period, advective fluxes average out to about 0.
So yeah, and it's we have another paper showing that the energy imbalance is linearly related to W star, which is convective velocity. So
Yeah, so great talk. It was really nicely described, and I love a good energy budget. I love to calculate energy budgets, so that was cool to see the application to land atmosphere fluxes. I'm kind of curious about this from like thinking of your what your hypothesis is now for what's given all this work that you've done. You kind of mentioned that there are different possibilities for what might be going on. It might not be the advective fluxes, or maybe there's something going on with the advective fluxes that you weren't able to resolve. What's your best guess as to where the imbalance comes from? Like if you were going to develop another field campaign, what would be your hypothesis?
I do think that advection is part of the story. Actually, I have some slides that I did, but I can go back and there are times during the study period when, if you look here, I have to unhide this. So this is a section that I just left out for time reasons. But the gray shows the advective fluxes and the black is the energy residuals. There are times during the study period for certain towers when you'll see really strong agreement. So that indicates to me that likely the advective fluxes are part of the story here. But then you see these other times when they have the opposite behavior. And there's something else going on there. And I think, I don't know, I think part of that might be issues with our W bar and again, that assumption of horizontal homogeneity within the control volume. I don't know, there are some things that I'm kind of like, I have theories about.
How does the horizontal inhomogeneity give you a systematic imbalance, though? It seems like a big part of the key to what the solution is it has to give you like a systematic imbalance.
Yeah.
And the kind of diurnal cycle plus vertical motions is like one reason why you expect a systematic imbalance during the day, but like, what are the kind of systematic possibilities, I guess? That's kind of what I asked during your talk.
Yeah. So, so one thing, if you think about, I don't know, this is something that I'm still like kind of very much working out. You have your flex tower, and you think about like, maybe you have an updraft by your flex tower that might be carrying warm air from the surface up in the atmosphere, you have surface heating. And so you kind of have air coming in the sides of your control volume that is then being warmed up as it travels across the surface and goes up. And in those cases, our calculated advective flux, because the gradient of temperature from the surface up to the top of the tower is negative, it's getting colder, that technically constitutes a negative vertical advective flux. And that, I think the issue there might be that like, if you have air kind of coming in, converging, in the sides, it might, like that, the air like that air is being warmed within the control volume, but yeah, and it's taking energy away, but like the way that we're calculating it, because we only have measurements at the tower, leads us to calculate a negative flux. And that, I don't know, that's something that I need to think about more.
There's a great review paper that just came out, and so part of this too is this idea, also if you think about it from a top-down perspective, which is that in the daytime, above the boundary layer is almost always warmer and drier, right? And so if you have larger scale impinging eddies, they are always bringing warmer, drier air down. And over a 30-minute averaging period, you would systematically always miss the warmer, drier air because you're averaging that out by taking out the UW bar, right? So that's the theory, that's the kind of the large eddy hypothesis. Here's the cool thing, if you run an LES at meter scale resolution at 10 hertz output, and you sample it like you were built a flux tower in it, you will get an energy imbalance, right? Like you can make an energy imbalance happen in a model, which means that it's real. Like it's not just that I'm bad at making measurements. I will readily admit I'm as bad as everyone else at making measurements, but there does seem to be something happening with larger scale transport. The other thing you can do is you can increase the averaging time. In the real world you can't because it's non-stationary, the sun moves everything. The model you can if you have fixed conditions, and you can improve the energy balance by increasing averaging time. So there's something to that larger scale transport. And our idea here was, could we capture it through looking at just gradients, because those should show up as gradients, but they don't systematically.
And it seems like something where there's a lot of room to do more modeling.
I think let's take one. I
analysis.
know Becca had her hand up earlier.
Yeah, with the issue like the heteronomy of like your spatial domain, why not just make a smaller spatial domain, like to more localize?
Yeah, well, so that's kind of what I was trying to do by decreasing the interpolation distance. But the fact is that we own, like, the towers we don't have the spatial like resolution in the measurements to really know what the gradients are at a smaller scale. And also we're trying to capture transport by these larger eddies, and so that's kind of happening on these larger spatial scales.
Did you have a burning question, John?
I just wonder if you stratify it by local weather type.
Yes, that is something that I have not gotten around to.
It strikes me that some of these advective fluxes in the vertical would be different on different broad
That's what
scale.
we talked about looking at other
characterizing the
charts.
weather, you know?
Yeah. One thing that is interesting is
I wonder about, like, we have Lake Superior 60 miles.
Yes, I did.
You might be able to see some, like, really well-defined, good to think about that.
when I did the sort of like case evaluation of just looking at a case when you have really good agreement between advection and energy residual, you don't see that consistently across all the sites. So that indicates that that like the reason that it's working well sometimes and not others might not be due to larger scale weather or something, but it's certainly worth looking into.
If you got some weird thing coming off Lake Superior and it affects the northwest part of your domain, that's different from the places in the southwest or northeast and southwest.
So, yes, and everyone is welcome to all open access, open source data on the NCAR repository, so go do stuff with it. But let's give another hand to Emily. Thank you.